The probability of an earthquake occurring at the same moment as the peak windstorm, at the same time that live load achieves its peak while simultaneously experiencing a record snowstorm, is almost zero. So instead, we design for certain combinations of loads. The load values we use for design are typically referred to as the maximum likely. Let's consider live load for offices as an example. Each office will experience a peak live load over the lifetime of that office. If we plot those peak values for lots of offices, we would get a probability distribution like this. The value we find in a code is chosen such that there's a sufficiently small probability that the peak is bigger. So the value would be somewhere like this. The probability that the actual peak is bigger than the number we use is the area under the probability curve to the right of the number. So this shaded area represents the probability that the actual live load gets bigger than the maximum likely value. Our goal as engineers is to make that probability reasonably small. Therefore, we amplify that maximum likely value with a load factor. The load factor effectively shifts us farther to the right on the graph, so the area under the curve to the right of the value is relatively small. But what if the probability curve for a different type of load looked more like this? If we amplify this maximum likely value with the same load factor, we will get a significantly smaller probability of the actual load being bigger. On the one hand, we like safety, but spending money to make one problem significantly less than another is not effective. The goal is to make all of the probabilities roughly the same, small but similar. Therefore, we use load factors to address the different probability distribution curve shapes for different load types. So, for load types that have a wide distribution of peak values, we want a large load factor in order to get a sufficiently small probability of the actual peak being larger than the value we use. Live load is in this category, so it tends to have a large load factor. For load types that have a narrow distribution, we can use a load factor close to 1 and still get a sufficiently small probability of the actual peak being larger. Dead load is in this category. The actual load factor values are decided by a committee after performing statistical analysis of available data. The likelihood that the dead load and live load on a structure reach their maximum likely levels at exactly the same time as the snow load reaches its maximum likely level is very low. But there might reasonably be some snow load at that time. We use load combinations to account for the likelihood of different load types reaching their peak at the same time. Some might be at their peak values while others exist at less than their peak. Therefore, some combinations use load factors smaller than 1 on certain load types. As an example, consider two combinations from the ASCE standard. The first combination accounts for the possibility that the dead and live loads achieve their maximum likely values, so the load factors are 1.2 and 1.6. There's a reasonable possibility of snow, but not its peak value. Therefore, the load factor on snow in this combination is 0.3. Our second combination accounts for the possibility that the dead and snow load achieve their maximum likely values simultaneously. So we use load factors 1.2 and 1. There will likely be some live load at that moment, so the combination includes live load but with a load factor of 0.5. Depending on the standard, there might be a dozen different load combinations that reflect what the committee considers reasonable likelihoods of occurrence. The design value or ultimate value is the internal force or reaction for which we design a member. That value is the largest of the factored and combined values. For example, if a beam experiences only dead, live, and snow load, we would determine the midspan moment due to the maximum likely dead load, the midspan moment due to the maximum likely live load, and the midspan moment due to the maximum likely snow load. We would then multiply the moments by the load factors in a load combination and calculate a value. We repeat the process for each load combination. The largest factored and combined result becomes the value we designed for. We calculate the design value for each internal force for each member of the structure. So there's not one governing load combination. The combination that gives the design axial force for a member might be different than the combination that gives the design shear value. And the combination that gives the design moment for one member might be different than the combination that gives the design moment for another member.